Welcome to another edition of Math Formalism. In this edition, we are proving this result that every polynomial with odd degree and real coefficients has a real root. How do you prove this result? So let us write down a polynomial. N is odd and a not equal to 0 is odd degree polynomial with real coefficients. Since an is not equal to 0, we can divide all through by an. So fx can be re-expressed. Now let us take x to the power n common. So we have, now let x go to plus infinity. So we make x very large, and in that case we have x to the power n goes to plus infinity. And observe that all these are 1 by x to the power n, 1 by x to the power n minus 1, etc. 1 by x. So x is in the denominator. So as x goes to plus infinity, all these terms go to 0. So the term within this bracket, that is a0 an to the power x to the power minus n plus a1 by an x to the power minus n plus 1, etc. an minus 1 by an x to the power minus 1 plus 1. This whole thing goes to 1. Therefore, fx goes to plus infinity as x goes to plus infinity. A very important result to note. Now what happens if x goes to minus infinity? So when x goes to minus infinity, remember that n is odd, like x cube, x to the power 5 and so on. So x to the power n goes to minus infinity. The other term, as x goes to minus infinity, again because this is like 1 by x to the power n and x goes to minus infinity, all these terms go to 0. And therefore, this term again goes to 1. So as x goes to plus infinity, fx goes to plus infinity. As x goes to minus infinity, fx goes to minus infinity. We will use these two facts to argue the presence of a real root. Since we are dealing with polynomials, so all polynomials are continuous functions. And this function goes to plus infinity when x goes to plus infinity and goes to minus infinity when fx goes to minus infinity. So something like this. So by the intermediate value theorem, or its special case, the Bolzano's theorem, we can conclude that the function would have a real root. Note that intermediate value theorem tells us that if you have a continuous function which is negative at one point and positive at some other point, then in between there would be a point at which the function would take the value 0. So we use this result to claim that there must be a point C such that fc is equal to 0. This proves our claim